Well, welcome to this particularly festive time. The Institute looks lovely and have a good turnout today. I hope everyone is safe on the roads. Thank you very much. Just wait for it. Excellent, thank you very much. So my name is Don Black. I'm on the Friends Executive Committee. And I want to thank you all for coming out this evening and also welcome our speaker. So Professor Richard York is here from the University of Oregon, and it's my pleasure to welcome him today. So he's this year's Friends of the Institute sponsored member in the School of Social Science. He's a professor of sociology and environmental studies at the University of Oregon, and he's a popular teacher, having received the Thomas Herman Faculty Teaching Award for distinguished teaching, as well as the Faculty Excellence Award in 2013. Dr. York earned his BS in psychology from Southern Oregon State College, a master's degree in environmental studies from Bemidji, I'm sorry, I knew I was going to mess that up, State University, and a PhD in sociology from Washington State University. He's widely published, including 3 books, Science and Humanism of Stephen Jay Gould, The Ecological Rift, Capitalism's War on the Earth, and The Critique of Intelligent Design, Materialism versus Creationism from Antiquity to the Present. He's also written numerous journal articles, book chapters, encyclopedia entries, book chapters, sorry, I had that twice, book and film reviews. His research and teaching interests include environmental sociology, human ecology, and ecological economics, political economy of world systems, philosophy, history, and the sociology of science, animals and society, research methods and statistics. And Professor York's current research examines how structural characteristics of societies, for example, demographic, economic, and technological factors, influence the quantity and types of energy use. He's interested in the extent to which development of non-fossil fuel energy sources displace fossil fuels and how this differs across nations. The title of his talk this evening is Looking Beyond Technical Fixes, a Sociological Perspective on Climate Change. Please welcome Dr. Richard York.
Well, hello, everyone. Thank you for coming out on this cold night. And I also want to give a particular thanks to the Friends of the Institute for funding me to be here. It really is a wonderful honor and privilege to have a chance to spend a year here at the Institute, so thank you very much. I think Don has given you a good sense of what I'm up to, so I'll just give brief orienting comments. I'm an environmental sociologist, and broadly speaking, that means I study the connections between society and the environment, both how environmental conditions affect societies and how societies affect the environment. And my particular interest, or one of my particular interests, is in energy use and related to global climate change, and particularly looking at not only how economic and demographic factors influence those, but also considering how technology influences our use of energy. And so today my focus is going to be particularly on energy use and specifically on fossil fuel use and what contributes to that use, or more what potentially suppresses it. I kind of take as a starting point that there's a legitimate interest in societies moving away from the use of fossil fuels. And I just as a starting point there being the very strong consensus among scientists that burning of fossil fuels contributes greenhouse gases, which are leading to changes in the global climate, which could have a variety of very serious effects. But I should also note fossil fuel use contributes a great deal to things like air pollution, most noteworthy, acid rain is part of that. And then there's a lot of impacts associated with the extraction of fossil fuels and transportation, such as oil spills and mountaintop removal mining for coal and so forth. So kind of the starting point of my talk is an acknowledgement that fossil fuels have very serious environmental consequences, and therefore a variety of good reasons we might wish to not use them. Now, I think one of the ways we tend to approach this issue, and we see this a lot now, particularly globally in considerations of addressing climate change, is finding out how to make this transition from fossil fuels. And I think mostly it tends to be framed and thought about as a technical problem. We tend to see our energy use as technical in nature that can be solved by developing new and improved technologies. And just to kind of tip my hand here, academic talks are kind of the opposite of mystery novels. We tell you our point up front so you're not surprised by it, and then we bring you back to it. My larger point is in a lot of ways we think incorrectly about seeing these as technological problems. Obviously, technology is vastly important, but technology is used by humans. It is embedded in social systems. So often you find the types of technologies we use and how we use them can lead to counterintuitive effects. And that's for all the reasons we find kind of weird things in societies. Societies are complex. There's a lot of feedbacks and loops. So there's nothing, there's very rarely a simple, direct, sensible outcome from things. And a lot of these are often very surprising. So in some sense, my larger argument would be that we should think of environmental problems as at least in substantial part, as social problems, meaning they have something to do with the kind of societies we have, the social processes we have, political and economic factors. So let me take then my two kind of technological issues and show some of the limitations of them. I think if you look at most discussions of what we should do to address climate change and move away from fossil fuels, two really stand out. And here I mean both in popular discourse, but among politicians, also among environmental groups, and often among climate scientists. First is to develop better ways of being energy efficient. Right? Fossil fuel use is tied very closely to our energy use. So we have a genuine interest in improving energy efficiency. And you can think of that on multiple levels. Energy efficiency in the sense of individual technologies like home appliances, cars, but also in a macro level sense, which you'll see is what I'm focusing on, the energy efficiency of entire economies, meaning typically energy used per unit of GDP. Meaning if you can produce an economy using less energy per dollar, that's macroeconomic energy efficiency. So that tends to be a standard hallmark of energy policies, is to improve energy efficiency. And the second issue I'll discuss is our other main approach tends to be to develop substitutes for fossil fuels, meaning obviously we're going to use energy if we can develop non-fossil fuel energy sources. The main ones in the world currently are nuclear power, hydro, wind, solar. There's also geothermal and tidal and a few others that play small parts. So that's based on the side if we develop alternatives in some sense, they'll kind of push out the fossil fuels. And just once again, to tip the hand, I'm going to actually kind of make the case today that both of those don't tend to work as well as we often would expect them to. And maybe I'm going to discuss some of the reasons why that oddly happens. So let's start with efficiency. It seems to me kind of obvious on its face, if improving energy efficiency should reduce energy use. For one starting point, kind of by definition, all else being equal, energy efficiency reduces use, because typically that's how we define efficiency. It's how much energy you use to produce a particular object, a widget, or whatever, or to produce a service, transportation, or once again in the macroeconomic sense, to produce a dollar of economic production, GDP. But, of course, efficiency does not happen in isolation, and it affects entire production and consumption systems. So you can have feedbacks where efficiency can be tied in with the scale of production and consumption, which can lead to some kind of paradoxical outcome. So let me just give a standard prime example. China. China stands out as this kind of major place we're concerned about for its energy use. Obviously, there's a lot of people in China. Its economy has grown dramatically. Now, I'll tell you two soundingly contradictory things. In one sense, China is a complete model of environmental reform in the sense that between 1980 and 2010, the energy efficiency of the Chinese economy, meaning how much energy it took to produce a unit of GDP, improved fourfold. I want you to reflect on that. That is an amazing improvement in efficiency, meaning in 2010, it took 1/4 the energy per dollar, or yuan, depending on which currency you want, of GDP than it did in 1980. I mean, that really is remarkable. or state that the other way around, unit of energy produced 4 times the more dollars 30 years later. So a remarkable improvement in efficiency. On the other side, China's per capita energy consumption increased 3-fold, and its total energy consumption increased 4-fold, obviously partly because of population and growth. Now, this also, you'll probably have known in one of the highlighted epochal moments of the past decade is around 2006. It's hard to say exactly because there's a lot of noise in energy data. China surpassed the United States to be the single greatest emitter of carbon dioxide in the world. And I say that's epochal since any reliable records have been kept, the United States has produced more carbon dioxide than any nation on Earth. And so to be surpassed. Obviously, the United States still emits far higher per capita, to be clear there. So I present this as an interesting phenomenon. China, both in the past 30 years, became much, much more efficient and used much, much more energy. Now, I want to tell you, I just used China as an example, that China is not unusual. In fact, China really is replicating the standard pattern of industrialization that has happened most places, most times over the past 2 centuries. That is actually not anomalous, but typical. I don't mean universal, that there aren't exceptions. There's going to be many exceptions to anything, certainly in the social sciences. But really just note that then, that China is not in any way odd. Now, this interestingly actually has been observed, this phenomenon of efficiency oddly being associated with rising use of a resource going back to the 19th century. And so famously, the kind of foundational ecological economist William Stanley Jevons noted this in his well-known book, The Coal Question, published in 1865, about coal use, that he'd noted as steam engines became more and more efficient, coal use increased, right? So hence it's called the Jevons Paradox now. More efficient steam engines, more coal use. And he actually provides a fairly straightforward and I think quite valid in its domain explanation, that he just thinks of from the point of view of a producer. If I'm going to invest in a steam engine, it has to be somewhat affordable. So if you have a very early steam engine that just takes mountains of coal to do the smallest bit of work, it's a very impractical machine. I would need to have my factories by a coal mine so I can ship all that coal there, and it's just going to be extremely expensive. And I'm probably not going to invest in that technology. Laborers are going to be a better deal. There's going to be something much better than coal. But of course, as coal efficiency improves, as you get more efficient steam engines, they all of a sudden become a lot more worth investing in and a lot more profitable. So as a simple sense, as you improve efficiency, you get this focus on coal-powered production. And I would add to that, of course, the profits you generate from that then give more money to reinvest in further expanding production. Now, I want to note then that that's kind of, I've noted a couple levels there, this kind of more industry level kind of contradiction of coal and steam engines that Jevons noted. I noted the pattern in China. Now, I want to note that, of course, that's correlation is not causation. So to say that high efficiency goes up, consumption goes up, that doesn't mean that there's a directly causal link. And I'll say from the start, one, this is not a universal pattern. There's all kinds of patterns, but it's not uncommon. Two, I don't think there's one reason. I think there are many. I think that some parts of it in many places are more coincidental. But I'll give some kind of, and I'll note one major non-causal reason is, or non-directly causal, is that improvements in efficiency and expansions of production are part of the same process. And this is a common thing if you think, once again, from the point of view of an industry trying to make profit. You know, 2 obvious ways to make more profit is I can produce more goods to sell. So I'm an industry, I try to expand production and consumption. I can also, I can reduce cost per unit of production. And one of the ways to reduce cost per unit of production is to make more efficient. So there's this parallel process going on where industries are trying to produce more and more and trying to lower costs per unit. Hence, you get this rising efficiency and rising use because, in a simple way of putting it, production expands faster than efficiency improves. So that's, I think, certainly something going on there. There's kind of two noted direct causal relationships, though, that are kind of non-controversial and, in a sense, standard economics, reasons where efficiency actually can increase use. The most obvious direct one is simply a simple cost logic. If I reduce the cost per unit of production or consumption, it makes it cheaper to use, so I increase use. So one example, there's lots of research on this. If you have a more fuel-efficient car, it makes it cheaper to drive, so it makes people drive a little more in aggregate on average. Right? I should note that tends to be a small effect. It tends not to overwhelm. It's not that, it's not that people will use more gas with a more fuel-efficient car. It's just simply that you won't get as good an improvement as you might expect based on efficiency alone. There's also a recognized indirect effect, and that's, in a sense, a fairly direct indirect effect. But simply, if you save money, so say, for example, you make your house more energy efficient, you pay a little less on your power bill, you save a little money, but that money is not sucked into the ether of the universe. You spend it on something, and the things you spend it on typically require some energy to produce. So there's kind of an indirect effect why saving money on energy leads to other consumption, which can counteract that to some degree. Now, those two are, once again, fairly straightforward, fairly non-controversial. And it's also well noted that those don't lead to huge effects. It's called a rebound effect by economists, meaning, if you get a 10% improvement in efficiency, it might mean you only get an 8% reduction of consumption, but you still get a reduction. That might be the kind of scale we're talking about from those. But the things I'm thinking about that I think need to be recognized in a larger kind of historical context are somewhat more indirect, but also I think part of why we find this common paradoxical correlation between higher efficiency and more consumption. I should actually just insert as a side note there that this not only happens over time, and you see in nations they tend to become more efficient when they consume more, it's very clear cross-sectionally. Meaning, generally speaking, the highest consumers in the world per capita are the most efficient, and the lowest consumers are the least efficient. So, countries in sub-Saharan Africa tend to be very inefficient macroeconomically, meaning they use a lot of energy per dollar, and places in Europe don't use so much energy per dollar, but per capita energy use in Europe is much higher than it is in Africa. So that's a common pattern. The central thing, though, I think that happens is efficiency in a larger sense affects the context in which production developments occur. So it changes the paths that people will follow, that development will follow, that industries will follow, that governments will follow. And I'll come back to an example of that. But I'll just also note that the other side, and this is similar to the indirect point I noted earlier about savings on money lead to more consumption, but also note that profits from industry, from efficiency, can be invested in the expansion of production. So in a sense, efficiency can lead to accumulating investment. But now I'll come back to illustrate the way that efficiency can make certain development paths more plausible that paradoxically in the long run can increase energy use with a thought experiment. I think I always like about thought experiments is they're not strictly speaking falsifiable, so I'm on safe grounds if you don't buy it, but I'll try to convince you that this seems plausible. So I want you to kind of think about car fuel efficiency, and I'm going to ask you to picture two alternative universes. So in one of these universes, every single car in the world is transformed into a highly efficient car. So let's say every car in the world magically becomes as fuel efficient as a Toyota Prius or some other hybrid, and let's just say gets 50 miles to the gallon, if you'll forgive me for using English units, which I really shouldn't do. I think, if Reagan hadn't come along, Carter would have got us to the metric system, but I'll stick with the English units. Because I think in the terms of them, because I was raised with them. So 50 miles to the gallon, one universe. An alternative universe is when we make every single car in the world extremely inefficient. And when I say extremely inefficient, let's make it the inverse of 50 miles to the gallon. Let's say it takes 50 gallons to go 1 mile. Right? So we have a 2,500-fold difference in efficiency. So here's the thought experiment. In which world do you think they would use more gasoline? Now, think about this case of the extremely inefficient world. So one thing, if it took 50 gallons to go 1 mile, your car would be all gas tank. I mean, this is going to be, You know, it's going to be hard to have a little seat for you up front, and you're driving this gigantic bomb. And now, presumably, with using that much gas, you know, it might suppress use and prices might drop. But I could just take the point there at current gas prices, depending on where you are, that's going to cost you maybe $150 to $200 to drive 1 mile. Now, so the proposal, I would say, is in that world, biking is going to sound a lot better. You know, walking is going to sound a lot better. But in a longer-term sense, you're going to have very different kinds of development. I mean, think about our development in the United States post-war of the kind of suburban commuter lifestyle. That's going to become, and we don't often think about that, but suburbs are really about cheap fossil fuel. And ironically here, efficiency of cars, that they somehow make it possible. Right? So I kind of give that extreme example to say, oddly, you know, and those are obviously huge extremes, that in some sense, one of the reasons we rely on cars so much is that they're kind of sufficiently efficient, not because they're so inefficient, and that leads us to use a lot of gasoline. Now, I don't wish to, my message here is not go out and buy a Humvee. Please don't take it as that. Because of course, this is an unnaturally wide range. I mean, you know, most cars we're talking about are in a very small part of that range, and I don't think that that's necessarily going to play out, you know, on any small scale. But the point I just want to make there is, in some ways, efficiency has allowed this to occur. Now, I want to note, to make this a little less counterintuitive, that this actually isn't that uncommon a phenomenon. And I'll note another example, which is kind of a thing for us who live in the United States to lament, is since 1950, for example, labor productivity in the United States has skyrocketed. So, like, labor productivity is how many dollars or units of production does each worker generate, right? So that's a standard thing, been happening a long time. Workers are vastly more productive. Another way of saying that is fewer workers can produce the same amounts, or the same number of workers can produce huge amounts of anything you talk about, steel, cars, whatever. So labor productivity improvements should seem to imply that we would need to work less. But of course, the interesting trend is Americans work more than they did in 1950. Right? So that's another common one, is our average working hours have gone up while our labor productivity has gone up. Right? And of course, what that means is we produce a hell of a lot and we have a lot more material possessions. But ironically, labor productivity didn't lead us to work less, which was a common vision mid-century, that, you know, that we'd be freed from labor by our machines. And if you'll forgive me a small anecdote, my wife and I live in Eugene, Oregon, which is an interesting kind of place in time. And so a lot of it was developed after the war. And a topic I'm going to come back to here in about 10 minutes is, mid-century particularly, but still, energy was very cheap in the Northwest because they built a lot of dams, particularly on the Columbia River system. So electricity was extremely cheap. So when they built, and it has pretty mild climates, I should note too. So when they built houses, efficiency was not what they were really thinking about. So we in our house, we have a 1958 ranch house. And this is quite common in Eugene. We have ceiling heat. I don't know how many of you are familiar with ceiling heat, this kind of aberration. So it's radiant ceiling heat. It heats the ceiling. Now, I'm not a physicist, I'm a sociologist, but I do have a general understanding that heat rises. Right? So this does not take some advanced engineering intellectual to see one of the problems with this. I think heating the floor is a very good idea. So, and I can say having that, your feet are cold and you feel kind of like you're having a hot flash quite frequently. So my wife and I our local power company will have someone come to you and talk about, you know, getting a new power system that could be a lot more efficient. So we brought someone in to discuss maybe putting in a heat pump, which would give better heat and be a lot more efficient. And there's lots of reasons why that's impractical, because we'd have to cut ducts in and it makes it very expensive and so forth. But what he said to me, and I thought was very interesting, he kind of just says this off the record, he's like, you know, ironically, a lot of times when people put heat pumps in, their energy consumption goes up. And why does it go up? Because currently with this awful ceiling heat, you only heat the rooms you're in. Heat pumps tend to heat the whole house very evenly. So people tend to heat the whole house very evenly, often to a better temperature. And the other big thing is, you know, most people in Oregon don't have air conditioning because it doesn't get hot in summer. But now a heat pump also provides air conditioning, so people start to air condition in summer. So providing this much more efficient heating system, as my power guy told me, often, ironically, leads people to use more energy. Right? So I just kind of give that as some ways to see that maybe this isn't, you can maybe see plausibly how this can happen. It's not just some kind of academic aberration that I'm talking about. Okay, now I'll move on from efficiency and come to my second issue, and that is the development of substitutes. Right? So I'm going to start off with a banally obvious statement. If we are going to not use fossil fuels, it is necessary to have some other energy source. Right? That's pretty obvious. We could certainly use less energy, but we can't use none. All societies need energy. So let's start there. Obviously, it is necessary to have alternatives if we're going to move away from fossil fuels. No problem there. But given these kind of strange feedbacks I've noted in societies that can happen, does that mean that just as things are, adding non-fossil energy sources to a society, a nation, leads to less fossil fuel use than they would have otherwise? And I would just say, one of the most basic implicit assumptions that people make is, well, of course, it'd be one-for-one displacement. Each unit I produce of energy from some other source of fossil fuel, I don't need the fossil fuel. I don't think even most of us would need to think of it that explicitly. It just seems kind of obvious. But there's actually kind of reasons why adding energy use might adding new sources might add on top of fossil fuel rather than pushing them out. And so before I get to this analysis, which is I said actually this talk is really at its core about some elaborate statistical econometric analysis, which I'm going to kind of hide all the very dull and boring parts, which would be almost all of it. So let's start with the potato chip analogy, as I call it. And I want you to think of an energy system. So my body is an energy system. I need energy to live, so I eat food. Now, here's a kind of a question. What if there was caloric displacement of our food? Because I only need 2,000 calories a day to survive. So come midday, after I've had my wonderful lunch over here at the Institute, 3 o'clock, I'm a bit peckish, and I eat a bag of potato chips that maybe has 300 calories. Now, here's the question. Is that going to displace what I eat at dinner? Do you think I will now eat less at dinner because I've eaten this bag of potato chips? It's provided 300 calories. I only need 2,000. Surely I will eat less at dinner. Is that how it works? Not for me, unfortunately. I mean, maybe some of you good people that are a little more restrained than me, but and we all know that too. The irony is I can have a full dinner and feel stuffed, and then dessert comes out, and I'm probably willing to choke that down too. So my point there is that calories oddly don't displace calories necessarily. They could in principle, obviously. I mean, I could live on much less. You know, I could live on 2,000 calories. They could displace it. But in practice, that's one of the reasons that some of us get a little soft in the middle, because calories often don't. And that's one of the curses of our modern comfort, is we've added all these great food options, so we eat more and more. Okay, so once again, I say that just to set you up to maybe say this isn't that odd of an idea. So what I'm really talking about here is a paper I published in Nature Climate Change in 2012. And in it, I do this statistical analysis of data for most nations of the world. So it's 132 nations, and that would include over 95% of the world's population. So what's mostly missing are small island nations and so forth. And over a 50-year period, so 1960 to 2009, the latest year of data I had at the time. And my question was this basic one, is in nations that used more non-fossil energy, do they use less, or do they use 1 unit less, 1 for 1, for each unit? So if each unit they produce a non-fossil fuel, do they use 1 less unit of fossil fuel? It's a basic question. And the statistical approach there is really just to model fossil fuel use on the standard things that energy economists use to model fossil fuel use. Obviously, GDP. I should note, look at per capita, control for population. GDP, whether they're a manufacturing economy, how urbanized they are, and other demographic things like their dependency ratio and so forth. And then add to that model how much non-fossil fuel energy they use. So in a sense, you're modeling how much fossil fuel use would I expect a nation to have, and then does it have somewhat less if I have non-fossil fuel energy? So it's kind of a simple logic, although I like to be vain and think I did a nice job of it. Now, I know I looked at this in two senses. I looked at it in the electrical sector specifically, because that seems the most focused. It's the most clear use of electricity. And I should note then, so as a catch-all, fossil fuels, I'm looking at kilowatt hours in the electrical sector generated by oil, gas, and coal. And alternatives, it's anything that's not those, but principally nuclear, hydro, wind, solar, and then once again, in a few places, you have some geothermal and some other, I should note biomass, biofuels. So I looked at this in the electrical sector, kilowatt hours, and I also looked at it in total energy use, kind of aggregates BTUs or whatever unit you want of energy. And in a sense, what the statistical analysis is trying to do, it's kind of trying to give us this controlling for to create something like an experiment. Obviously, it's not a true experiment, so there could always be many factors we missed that could explain these. But that's to say, if you have two nations that are basically the same in this kind of hypothetical statistical abstraction, they have the same populations, the same GDP, and so forth. And over time, all those factors grow at the same rate. But then one of them adds non-fossil fuel energy and the other doesn't. Does the one that adds non-fossil fuel energy uses much less fossil fuel as it added non-fossil fuel? It's fairly straightforward. Okay. And note, in a lot of ways, when I say displacement, that could be suppressed growth, because mostly over this period, most nations are growing in their energy use. So a displacement would be, it might have grown, but it would be less than we would expect otherwise. Okay, so here's what I found. There is displacement, but it's very, very small. In the electrical sector, it's approximately 12 to 1, meaning all else equal, if you add 12 units of non-fossil fuel energy, you tend to seem to displace only 1 unit of fossil fuel energy. It's a little better in total energy, varying on models, kind of 4.5 to 1 to 8 to 1. Another way of putting that, let's say 5 to 1 is probably a good sense, is it took 5 units of non-fossil energy to push out 1 unit of fossil energy. So there's displacement, but it's very small, meaning to a large extent, when we add alternative energy sources to power systems, to energy systems, they tend to add on top of the fossil fuel, and fossil fuel keeps doing what it would do anyway, approximately. I mean, once again, there is some displacement, but it's very small. Now, that, once again, I kind of warm you up with a potato chip analogy to say, yeah, that's kind of counterintuitive, but I think there are sensible reasons that happens. And hopefully that's what I'm going to finish off the talk here with kind of giving you those reasons, and hopefully you'll find that compelling. I should note that, of course, my analysis only establishes this kind of fact as an empirical claim of non-displacement. It doesn't tell me why. So I'm ad hocing here. I'm trying to give some reasons I think this is the case. But strictly speaking, the model just says that's what we observe. So why might that be? And I should give that similar disclaimer I gave earlier, that I think there's many reasons for this. I think it probably varies across time and place. I don't think there's one explanation and one answer. I certainly don't think it's inevitable. That's another important message I would say. I don't think it's inevitable that this happens. It seems to be common. And it really is just a general pattern abstracted across nations. But I think the reasons here are kind of, a lot of them are social, political, and economic. So let's start again with the most banal and obvious reason. So one is just a simple economic logic. All else equal, if I add supply of energy, it reduces costs, so it spurs demand. That's a standard one. So that's not surprising. So if I didn't add that energy, there would be more energy constraint. It would increase costs and suppress use. So that's probably going to have a bit of an effect. Some other fairly obvious kind of social political ones are, just taking a straightforward political statement, the fossil fuel industry is very entrenched. It has a lot of political power across nations. It has a lot of money, provides a lot of jobs. And of course, it also just has a lot of literal physical infrastructure. There's oil pipelines, gas pipelines, and so forth. And given that, you think about how politics works. Political processes, I don't mean to disillusion anyone, but they don't tend to work very rationally, and they tend to politicians do strange things, and they do strange things for their strange interests, right? But it tends to be that entrenched industries, if they have, their constituents want jobs, they want funding for re-election, they tend to protect entrenched industries. So I think something is going on there is just fossil fuel industry has momentum. We have so much set up to use fossil fuel. Even if we add non-fossil fuel sources, we keep using the fossil fuel. It's just very dug in. But okay, I'm going to come to, I think, going to the less obvious reasons, I think a lot of the reason we expect that adding alternative energy will displace fossil fuel is that we have an implicit demand side assumption. We kind of tend to think, like I gave with the body analogy, I assume that a society just needs a set amount of energy. So if you fill that need up with one source of energy, it won't use another. And that if the potato chip analogy wasn't true, right, I eat the potato chips, I just eat less elsewhere, I'm just a fuel system. But I think that the issue here really is, in a lot of ways, supply drives demand. So in some ways, that's my bigger abstract point to say is we shouldn't really think of these as purely demand-driven. We produce energy because it's needed. In a lot of ways, we need energy because it's produced. I should note in a very crude sense that's called Say's law, but Say's law from economics, but Say's law is actually very much more specific, so that's why I wouldn't per se characterize that claim as strictly Say's law. So there's one obvious way this happens that won't surprise anyone. Corporations have long recognized that suppliers can create demand, and that is hence the past century or more of the development of the advertising industry. That was very explicitly acknowledged early in the industrial era that producers could produce so much because of the use of fossil fuel. They could supply so much that the problem was getting people to buy it, so they had to have all these mechanisms in place to spur up demand, to make people need things and want them so they could supply them. So that's also, I think, probably not that controversial in a way that suppliers work to create demand very explicitly. But I want to kind of come to, somewhat even a more general process that happens in societies. That all businesses, all individuals, all politics happens in contexts. And when we change the technological infrastructure, we change the context, and that changes the way decisions are made. And in a lot of ways, making more energy available changes the context, which changes people's calculations to be more willing to invest in using energy. So I'll just give this as some historical examples. So I'll return to my ceiling heat and the cheap energy in the Northwest. So I want you to think about this amazing phenomenon. The United States built an awful lot of dams in the 1930s. And typically these are hydroelectric dams. This is an amazing fact because this is the middle of the Great Depression. Right? This is not a roaring economy that's expanding and demanding energy. And I give the obvious reason. The funding of the dams, a lot of the dam building happened through the WPA. It was very much an effort to provide jobs, very explicitly so. Right? So it was not a case that you had a huge demand for energy out there, per se. It was you had a huge demand to put people to work to do things that led to supplying energy. I should also note dams were built for a lot of reasons, and a lot of times the hydroelectric was only part of that. There were a lot of motives. So some of those are obviously flood control. They allow barging on some rivers, irrigation systems, and so forth. So my point is, if you think about that, really the dams and the energy they produce came first, and then the use came second. And I'll give a lot of what happened there was they put in all the ceiling heat that is tiresome, but also in industry sense, many energy-intensive industries developed new production facilities by the dams because the energy was cheap. One of the major ones was aluminum smelting. Right? Aluminum, it's an electrolytic process, at least the Hall-Héroult process that was developed in 1886. It's very energy intensive. It's a simpler process than the old process, but it's very energy intensive. So a lot of aluminum's price is directly tied to energy prices. So you had this development of aluminum industries and many other things near the dams. And the irony is actually, in a lot of ways, that not only did those dams not displace fossil fuel use, in some ways they increased it, because when you build all these factories out, a lot of this is in Eastern Oregon and Washington, which is kind of remote. They tended to build more roads, they need more shipping, more trains, more trucks to bring products to and from the production processes. So there's this kind of strange process where we build the dams first. That gives us a lot of energy. We build industries to use that energy, and those industries make us need more fossil fuels. Now, I don't want to say that that's per se typical, But I think there's common examples. So I'll give another one that's kind of interesting. Think of the controversy over whaling. This has always been an interesting question, right? So we understand whales through a lot of human history up until the latter part of the 19th century. One of the major reasons people got whales was for whale oil, which is the central for lighting. It was used in lamps and many other uses. But whale oil was a very key energy source in the world, right? Which is an interesting thing. We don't think about that. It's very much an energy source. Now we would think that the development of fossil fuel should kind of make that passé, because it does seem terribly inefficient to hunt the world's oceans, to catch these whales, to boil them down, to get oil to ship. It seems kind of remarkable, actually, if you think about it. Now, here's an interesting fact, though. And there's been a lot of discussion of this often called the whale oil myth in the 19th century, of how this actually doesn't happen. You don't actually see petroleum pushing out whale oil. But I'd actually like to bring us to the beginning of the 20th century. At the beginning of the 20th century, there was kind of the quote-unquote discovery of the Antarctic whaling grounds. Right? There are a lot of whales in the southern oceans. And these weren't really accessible until then by European powers, Northern Hemisphere powers. They're far away. The Antarctic wasn't easy access. And there's tons of whales there. And there's tons of really big whales there, like blue whales. And blue whales had not, until the 20th century, typically been hunted by whalers. And one of the reasons, at least, they had not, is they swim faster than sail ships. So whalers couldn't catch them. There's also the fact that the development of the Foyne cannon, an exploding harpoon cannon that could kill and help pull in a giant whale. Now, here's the irony. The development of fossil fuel-powered ships let ships go fast enough to catch blue whales and other large rorquals, and it made it feasible that they could then ship them more expediently back up to most of the markets in the Northern Hemisphere. So there's this kind of strange irony that the development of fossil fuel use, the expansion of petroleum use, not only did it not push out whale oil and whale products, in some ways it actually drove it. And there were a lot of new uses found for whale oil. And I would say they're very genuine uses, but they're all potentially substitutable. As you probably know, whale oil was commonly used in paints, particularly for marine paints. A common lubricant that was used in automatic transmission lubricants into the 60s. As another interesting note, that it was used on the lunar lander. It's a particularly good lubricant. It's used in intercontinental ballistic missiles. Pharmaceuticals, there's hundreds of uses for whale oil, all of which can be substituted by other products. So you have this strange thing by the fossil fuel makes it easier to get whales, so we find more use for whales and it expands use of whales. And really in the end, the sad story is that whaling mostly only ends because the whale populations become so suppressed they're not economically viable. So I think it's not that uncommon a case where development of potential substitutes ironically doesn't lead to suppression of what they substitute for. And I'll just use one last obvious energy part. Wind and solar power have as one of their virtues that they can provide energy to locales that it's hard to get power lines to. And that has many virtues to the people that gives power to. But I would note that that's a clear example where adding those types of energy sources is not displacing any energy source. It's a brand new energy source in a brand new place. So I think these are kind of some of the reasons why we would see the rise of non-fossil energy use, not per se pushing out fossil fuels. They're adding on top of them because energy is kind of useful and people find uses for it. You produce more. There's a lot of reasons it can be used. I think there are probably many other reasons. One I would throw out, which maybe has not acted too much historically, but may more in the future, is the fact that the kind of perception of particularly things like wind and solar is seen as kind of green may kind of suppress inhibitions on energy use. I remember, to give a secondary anecdote, a colleague I know was talking about interviewing people on their home energy use. And she noted to one woman who lived in a very big house and had solar panels on it. This woman drove a really gas-guzzling car. And the woman said, I have solar panels on my house. I can drive any damn car I want to. Right? In some sense, there's some sense the potential, and I mean that not in a micro sense, but a macro sense, that there's a lot of political pressure against energy use because environmental groups recognize it as a problem. But ironically, the development of green power can also lead to more of a tolerance of increasing energy production and consumption. And I'll just add just a couple quick larger issues that, of course, alternative energies are profitable. They're not done by saints who are doing this in a charitable sense. They're done by businesses. And ironically, many of the businesses that are developing alternative energies are the same ones who develop fossil fuel use. And so ironically, profits generated in alternative energies can be invested in oil drilling or other uses. And that's and even if they're not in the same company, that's a standard economic point. Money is very fluid through economies. So where it's generated has no necessary connection to where it's invested. Now, this shouldn't surprise us. I'll actually, quick examples, this happens a lot. One, the common discussion going back at least to the 60s, that computers would lead to paperless offices. Right? And it was often noted that paper use steadily rose since the 60s. I should note it started a downturn in 2007 with the economic collapse in North America and Europe. Global use still goes up dramatically. But there's that kind of irony that more computers led to more paper use. Even though it seems like they shouldn't. It shouldn't. Another common observation was the relationship of building roads to car use. That was a common, traffic engineers often note this problem, is they'd have traffic jams, so they'd build more roads. And so that's, people had a lot of reasons if there's a lot of traffic jams to not drive, but you build a new road, that makes it so they can drive, and often they found it can actually literally balance out. That people will expand their driving to fill the roads, right? It's kind of if you build it, they will come. So I want to note that that's actually not that uncommon a phenomenon. So just to kind of wrap up then, my point is not that technology doesn't matter. It's certainly not to say that we shouldn't be developing non-fossil fuel energy sources. As I said, I really hope you're not going to rip the solar panels off your roofs and buy a gas guzzler. But it is to say that we shouldn't just think of environmental problems in this technical sense. We have to think about how the technologies will actually be applied in real socio-economic systems. And I'll just give this kind of one final example. Think about the CAFE standards in the United States and energy use in cars, right? So the corporate average fuel economy. We have laws that say any company that sells cars in America, the fleet must have a set gas mileage average. And I want you to see this strange phenomenon. Between the 80s and the 2000s, there's, of course, huge technological advances in car industry, right? I mean, they shift from all those, I always grew up with crappy mid-century American cars that have carburetors. Cars all shifted to fuel injectors. They get very high tech. We make lighter materials. In many ways, the technology dramatically improves in cars. Right? I mean, in a lot of ways, they're very much more efficient in the sense that they can move more mass further. But the irony is actually the average gas mileage in cars actually gets a little worse from the 80s to the 2000s. And there's obvious reasons is we converted all that efficiency into bigger cars, and a lot of that was the shift to SUVs. So that's a pretty straightforward one. So I would say that in that sense, just improving efficiency did not lead to improvements in fuel use. The obvious statement, though, is if we had continually moved up the CAFE standards, that would have forced companies to convert those improvements in efficiency into less fuel use. Right? So my point there then is you have to think of that as, and that's a very simple sense of a social context. It's a direct policy. That's a fairly easy one. I'm actually thinking probably more broadly and less direct than that. But then to say the technology in and of themselves don't operate in isolation, we can definitely make sure that energy efficiency and alternative energies do lead to less fossil fuel energy use. But that still depends on social processes, political decisions. It doesn't just kind of naturally happen. And I will stop there. Thank you, everyone.